Hello viewers. The planning and design of large caverns placed side by side require a scientific analysis to base the designs on. Each such case in young Himalayan poses a completely different set of geological challenges and therefore cannot be designed merely on empirical basis. The lapses in geological investigation, planning of layouts, and detailed designs can be catastrophic in such cases. In this case study, I am going to present the chain of critical lapses which ultimately led to the Ravelling failure of rock mass, which formed a huge cavity of a size of a football field and of one third the height of the Eiffel Tower to the crown of the cavern of Downstream Surge Gallery of Punatsangchhu II Hydroelectric Project in Bhutan. The crown of the Downstream Surge Gallery, having excavated and supported since 2013, the massive rock mass failure occurred after 3 years on 3rd March 2016. Unfortunately, 6 technicians got buried dead under the failure falling muck. Billions of rupees got wasted, and uncertainty of completion of the project with 6 years of delay as of December 2022 crept in. During the presentation, I'll be making reference to a number of international literature and also to findings of Norwegian Geotechnical Institute in their case study taken up by them, and also I'll be referring to 3D numerical analysis done by National Institute of Rock Mechanics, India. The Punatsangchhu-II hydroelectric project was originally studied and designed to be a surface powerhouse in the detailed project report. However, during April 2010, just before taking up the construction of the project, a crucial decision was taken by the consultants of the project to shift the powerhouse complex location to an underground location 3.1 kilometer inside the right hand side hill of the river valley. This necessitated introduction of a 3.1 kilometer length of tail race tunnel, and also it necessitated to introduce a downstream surge gallery. Thus, the powerhouse location was changed from the DPR approved surface powerhouse to the underground as decided by the consultants WAPCOS and the design consultants Central Water Commission. The first of the crucial lapses had happened during May to October 2010 when, during the geological investigations done by the consultants for deciding the underground location, a lacking and misrepresentative geological investigations done by consultants had landed the powerhouse complex to an unsafe underground location. The 314-meter long downstream surge gallery site was investigated by the consultants who decided the change location based on their merely one borehole DSC1. The other borehole DSC3 was driven by the consultants at a different and faraway location to that suggested by their own geology consultants, Geological Survey of India. The downstream surge gallery had actually encountered intersection by mega shear zone, which was far away from the borehole DSC1. Actually, all the 3 caverns, that of powerhouse, transformer hall, and downstream surge gallery, were to be intersected by the mega shear zone, which was missed during the geological investigations while deciding the new location of the powerhouse complex. The second of the crucial lapses in planning and design had happened during December 2010 when, after a limited geological exploration done for deciding the changed location, the designers had decided a huge 314 meter into 58 meter into 19 meter sized Downstream Surge Gallery, despite a warning having been given by their geological consultant, Geological Survey of India. That resulted in a very frangible structure for Downstream Surge Gallery. The Geological Survey of India had reported in 2010 that a shear highly fractured zones may be encountered in the surge cavern. They strongly recommended to minimize the size of surge chamber as far as possible. CWC, the designers, had still provided, despite this warning, the huge size of 314-meter long, 58-meter high, and 19-meter wide size of Downstream Surge Gallery. Due to the limited and misrepresentative geological explorations done for deciding the changed location, the geological interpretation had gone wrong. The designers had considered, as interpreted from the limited geological exploration, a fair to good quality of rock to be available in the three caverns. However, actually, the geology came out to be poor to very poor against this interpretation of fair to good considered by the designers. The actual geology comprised of leucogranite with micaceous quartzite, biotite gneiss, and pegmatite veins bands, which were low dipping foliations with clay coatings. Significant length of the caverns comprised of class 5 loose rock mass, which was thinly foliated, highly fractured biotite gneiss with leucogranite and crushed pegmatite, Q value 0.19 to 0.58, where excavation progressed by chipping and scaling and no blast. This class 5 rock was encountered in Downstream Surge Gallery more significantly, and a major portion of the length of the Downstream Surge Gallery comprised of class 4 altered rock mass with Q value 1.5 to 2 with thin shears and seams, and sheared, crushed and fractured rock masses which were highly jointed with clay coating alongside intersecting joints. Excavation progressed with 0.18 to 0.36 kg per cubic meter of charge in this reach. Slabbing and wedge failures were predominant in this reach. Downstream Surge Gallery had actually encountered 14 shear seams of size 2 cm to 3.5 meter. 7 numbers of major joint sets were encountered, including foliation joint with low dip and direction of 10 degree to 15 degree southwest to northwest, spacing of 0.02 to 0.3 meter. Joints which were subvertical and adversely oriented for wedge actions have continuity of 10 meter to 15 meter and are generally altered and stained and show warping, which are filled with silty and clay material, sometimes also filled with crushed matter which have 10 mm to 20 mm opening. Thus, the third crucial lapse had happened in December 2010, that is, when the designs and more importantly, the layout designs were based on wrong geological input. The actual geology encountered, as well also evaluated by Norwegian Geotechnical Institute in their report, was found to be only very poor to poor in contrast to what it was assessed and designed for as fair to good. It can be seen that there were no trace of good and fair rock as was assessed during the geological investigations. Powerhouse cavern had 54% of it as a poor rock and 44.8 only poor to fair. Transformer hole cavern had 57% as poor rock and only 36% that too poor to fair. The Downstream Surge Gallery had 54% of it as a poor rock and 5% of it was very poor, that of class 5 and shear zones, and only 42% comprised poor to fair. There was no trace of any fair to good rock, which was making the basis of the designs, including more importantly the layout design of the powerhouse complex. Excavation of the powerhouse complex was started in 2012 with construction of main access tunnel to the powerhouse and construction added to the Downstream Surge Gallery taken up in 2012. A shear zone met in the construction area and the main access tunnel to the powerhouse in 2012. The resident geologist of the project apprehended that if the shear zone didn't get pinched, it will cut across the three caverns of powerhouse, transformer hall, and downstream surge gallery. Accordingly, the same shear zone, which was apprehended in 2012, did meet the three caverns in their central gullet in April 2013. A 3.5 meter thick major shear zone was encountered at RD 124 meter of the downstream surge gallery, which had inclination of 45 degree to 60 degree and an orientation of north 30 degree east, which was cutting all through above the crown to bottom of the downstream surge gallery. It resulted in formation of a hanging wall, and a 9 meter high chimney was got made in the downstream surge gallery's central gullet at RD 124 meter. This necessitated to change the layout and design of the three caverns in April 2013, when the revelation of major shear zone in downstream surge gallery's central gullet had happened. The designers, taking heed of the suggestion of the resident geologist of the project, did alter the layout of the powerhouse and transformer hall caverns by shifting the two caverns, that is of powerhouse and transformer hall, by 36 meter and 80 meter respectively to the southern end of these caverns, thereby to avoid their cutting by the major shear zone to a great extent. Excavation of the three caverns was started from their southern ends. The starting point of excavation at the southern end in the downstream surge gallery was accessed earlier than the starting point of excavation in the powerhouse and transformer hall. The excavation in central gullet in the downstream surge gallery was thus progressing ahead of the excavation in the powerhouse and transformer hall. The major shear zone was therefore met in the central gullet in the downstream surge gallery at RD 124 meter, while the excavation in the powerhouse and transformer hall had yet not progressed to those reaches where the shear zone would have been encountered in powerhouse and transformer hall, respectively. The resident geologist of the project suggested to the designers at that time that in order to avoid the cutting of the three caverns by the shear zone, their layout be altered and it be redesigned. Partially agreeing to this advice of the resident geologist, the designers had altered the layout but of only powerhouse and transformer hall by shifting these two caverns towards south by 36 meter and 18 meter respectively. However, the layout of the downstream surge gallery was left unaltered and was thus left to be intersected in the middle of the downstream surge gallery throughout its full depth of 58.5 meter by the shear zone. The hanging wall reach, which was following the shear zone in the downstream surge gallery, comprised of multiple set of joints, fractured rock mass, with joints filled with clay and crushed material. At that time, during April to December 2014, a crucial decision should have been taken by the designers for avoiding the downstream surge gallery to be cut by shear zone. As the function of the downstream surge gallery is only to provide enough volume which can supply efficiently water to the tail race tunnel on sudden shutdown of the turbines, and also can accommodate the discharge coming from the turbines immediately on sudden start of the turbines before it is gradually released in the tail race tunnel. This function can be achieved by providing an interconnected set of smaller chambers with equivalent volume of the one huge downstream surge gallery. The project management had at that time suggested to the designers that in order to avoid cutting of the downstream surge gallery by the shear zone, it can provide a distributed arrangement of smaller interconnected chambers instead of one huge cavern. However, the designers preferred to keep the huge size of the Downstream Surge Gallery and did not alter the layout of the Downstream Surge Gallery too. Having shifted the location of the powerhouse cavern by 36 meter and transformer hall cavern by 18 meter, the major shear zone was thus ensured to be merely touching the gable ends of both powerhouse and transformer hall caverns. Therefore, there was no hanging wall thus present in both powerhouse and transformer hall cavern, and this was a big plus point for the stability of powerhouse and transformer hall cavern. However, as the major shear zone was to definitely intersect steeply the downstream surge gallery throughout its full height, it would have been imperative to establish the stability of downstream surge gallery cavern scientifically through a detailed 3D numerical modeling in 2014 itself, when only the excavation of center gullets was completed in all the three caverns. It should have been done before proceeding further in its excavation in side slashing and further benching down to its full depth of 58 meters. 3D numerical analysis incorporating actual joint sets, shear zone present in the downstream surge gallery cavern therefore was needed to evaluate the structural stability of the caverns. However, it seems the 3D numerical analysis was not done by the designers and only symptomatic spot treatments were recommended by designers, ignoring impending displacements and stress distribution which would happen ensuing the excavation in huge benching depth of 58 meter. It is apparent that the 3D numerical analysis was not done throughout the stage of excavation of these three caverns during the period of April 2013 to March 2016 when the mishap had happened. It was only in 2018, after the mishap only, the National Institute of Rock Mechanics was roped in to do the analysis at the request of the project authority. The original design, which would be based on the input from the misrepresentative geological interpretation, was merely augmented by symptomatic addition of a few spot rock bolts here and there in the crown of the cavern and a dental treatment recommended in the walls at the portions cut by the mega shear zone. The basic character and methodology was found to have not been revised or changed, seemingly having no scientific analysis done of the situation in the downstream surge gallery. This was the fifth crucial lapse of not performing a 3D numerical analysis which should have incorporated the actual geology revealed in the excavation. This approach must have resulted in unsafe design as was realized from the 3D analysis done later in 2018 after the mishap, which shall be discussed later in the slides. It may be seen that during the excavation, the joint sets as shown in the given table under the column titled as encountered actually during excavation, that the joint sets J2, J7 and J6 were not realized to be present in the misrepresentative geological interpretation on which the designs were based. Incidentally, these three joint sets are not even represented in the 3D analysis done by National Institute of Rock Mechanics in 2018 either, and as such, these three joints remain not considered in the designs too. Thus, all the actually present joint sets which would have made the stability of the hanging wall reach, which followed the steeply dipping traverse of the major shear zone, had remained unaccounted in the designs of the downstream surge gallery. The criticality of these numerous joint sets and the major shear zone together, resulting in formation of potentially unstable wedges due to their dip, which was steeper than the angle of internal friction of the rock mass, is depicted in the stereo net shown here. The 8 types of sets of wedges formed out of the intersection of vertical and subvertical joint sets, which were actually present, with made out of intersection of joints J2 and J3, J3 and J7, J5 and J7, J2 and J5, J5 and J4, J3 and J8, that is shear, J3 and J4, and J3 and J6 are all very critical and potentially very unstable. These joint sets which form these wedges are vertical and subvertical and are much steeper than the angle of internal friction of the rock mass. With the presence of crushed material and clay in the gaps of these joint sets, they make a large zone of stress relieved rock mass. International literature cautions that large numbers of adversely oriented joint sets would result overbreaks and loose rock falls. The published international paper titled 40 Years with the Q System in Norway and Abroad, authored by Nick Barton, Einstein Grimstad, makes the important interpretation from the joint set number and a joint roughness number parameters of NGI's rock mass quality index Q. The paper recognizes that in underground excavation, where the ratio of joint set number and joint roughness number, that is Jn by Jr, exceeds 6, the overbreaks are extremely likely to occur despite contractors' best efforts with careful blasting. In Punatsangchhu-II case of powerhouse caverns, the ratio Jn by Jr is of the order of 9 to 12. This explains the prevalent tendency of overbreaks and slabbing falls in these caverns of Punatsangchhu powerhouse complex, despite that the excavation progressed by merely chipping without resorting to any blast in the reach of class 5 classification of rock mass and only resorting to 0.18 to 0.36 kg per cubic meter of charge in the case of class 4 reach of the caverns. This slide shows a typical slabbing and wedge failure encountered in the Downstream Surge Gallery crown in reaches with rock mass of class 4 classification. For the kind of tendency of the rock falls frequented in the 3 caverns of the powerhouse complex in Punatsangchhu-II project, there is a very relevant reference in the very well-known authors Hook and Brown's book titled Design of Underground Excavations in Rock. In this book, they state that in hard rock masses with strongly developed inclined structural features, excavation stability may be dominated by gravity falls and sliding along inclined discontinuities. Therefore, the rock classification systems may be inadequate to handle these kinds of situations. The authors have advised that to evaluate influence of the structural geology on stability of underground structure, one needs to check whether the underground structure is subjected to instability due to adverse structural geology. With the availability of modern analysis tools nowadays, a 3D numerical analysis is the best method to check the stability of the underground excavations. So, if the analysis finds that the adverse geology is causing instability to the underground structure, then the authors recommend that a second check is advised, which requires to evaluate whether the stability can be improved by relocation and or reorientation of the excavation If the stability is seen to be not improved by relocation or reorientation, then it recommends a third check to be made, that is, if adequate rock support can be designed to improve the stability, and however, if no design measures are seen to be feasible to improve the stability, then, as per the renowned authors, the only recourse left is to abandon and reject the site due to its adverse geological structure. The Q-based design practice develops an arch action and strengthen a very localized stress relieved zone in the rock mass. Steel ribs come into action only when need to provide a limited passive support to the backfill concrete or the limited localized rock mass volume. In the geological conditions such as found in Punatsangchhu-II project in powerhouse complex, which had multiple strongly developed inclined structural discontinuities, the designers should have checked the stability of the three caverns with a 3D numerical analysis, which they obviously did not do till after the failure when they hired NIRM, the agency, to perform a 3D analysis. As seen in the results of this 3D analysis, that the Q system based design provided by the designers resulted in extensive yielding of the rock mass, causing stress relieving to greater depths in the rock mass and developing tensile stresses above the crown in the downstream surge gallery with increase in depth of excavation in the downstream surge gallery. Had the 3D numerical analysis been done at right time by the designers before proceeding with the deeper excavations in the downstream surge gallery, the designers would have realized to either augment the designs or change the layout of the downstream surge gallery or even reject the site as advised in the literature by Hook and Brown. The designers were requested at least 29 times during the year 2014 in the various project review meetings held with the chief design of the consultants, and also mentioned to various geological notes supplied to the designers telling about the criticality of the geology and requesting to take a review of the designs, but to no avail. However, the sixth crucial lapse happened when in December 2014 the designers ignored the warning and just trashed aside the numerical analysis carried out by the concerned civil contracting agency of the powerhouse. This numerical analysis had established that with the given designs, the downstream surge gallery will become unstable with widespread massive yielding of the rock mass in the rock pillars of the downstream surge gallery when the excavation would reach towards two-thirds height of the downstream surge gallery, that is around 35 meters of its excavated depth, and that there will be further yielding reaching around 100% yielding in the walls of the downstream surge gallery when the excavation further proceeds and reaches the full depth of 58.5 meter of the downstream surge gallery. However, the designers, trashing the results of this analysis, went ahead without bothering to do a 3D analysis themselves at that time and redo the designs, which was much needed. It is ironical that the massive rock mass failure did indeed happen when the excavation in the downstream surge gallery had in fact reached to a depth of 35 to 40 meter of excavation, that is around two-thirds of the height of 58.5 meter height of the DSG. This slide shows the results of the numerical analysis done by the contracting agency and conveyed to the designers in 2014 December. It shows how with the increase in the depth of the excavation, the massive yielding will take place in the rock pillars of the downstream surge gallery. The left side diagram shows the extent of the yielding that would take place in the intervening rock pillar between the transformer hall and the downstream surge gallery when the excavation depth would reach two-thirds the height of the downstream surge gallery, that is to a depth of around 35 to 40 meters of excavation. And the right side diagram shows the extent of yielding that would be happening in that very intermittent intervening rock pillar between the transformer hall and the downstream surge gallery when the excavation of the full depth of the downstream surge gallery would have reached. As a widely accepted practice, which was brought out in a paper authored by Shang Wai and Lee, published in the 6th Congress of ISRM held in Montreal, the pillar width between two adjacent caverns should be equal to or more than the depth of the deeper cavern of the two adjacent caverns. The pillar thickness between the downstream surge gallery and the transformer hall in the Punatsangchhu-II powerhouse complex is only 40 meter as compared to the depth of the downstream surge gallery of 58.5 meter. Thus, even for the normal rock mass conditions, the rock pillar should have been having a thickness provided of 58.5 meter, that is equal to the depth of the deeper of the caverns, that is downstream surge gallery. And moreover, under the prevailing geological conditions in the downstream surge gallery, having class 4 and class 5 rock mass, and also where the downstream surge gallery is intersected through its full depth by the shear zone, the provided thickness of 40 meter for the rock pillar between downstream surge gallery and transformer hall was far below the requirement as stipulated and going by the accepted practice of having a requirement of 58.5 meter at least. This slide shows the progress of excavation in its various stretches and depths in downstream surge gallery. The shear zone is seen cutting the upstream and downstream walls of the downstream surge gallery sharply in the crown and below in both the walls to its full depth between RD 130 meter to RD 180 meter. The shear zone thus created a pre-cracked section of the rock pillar and the downstream wall in the downstream surge gallery. The northern block of the pre-cracked section lying over the southern block was free to slide on this steep shear zone. As a result, in November 2014, when the depth of excavation had reached in downstream surge gallery merely to a depth of 15 meter, a subsidence of 55 mm occurred in the downstream wall of the surge gallery between RD 130 meter to RD 170 meter, and a subsidence of 20 mm had occurred in the upstream wall of the downstream surge gallery between RD 170 meter to RD 180 meter. The upstream wall of powerhouse complex and the rock pillar between the powerhouse cavern and the transformer hall cavern were more vulnerable with multiple openings in them, that of pressure shafts and bus ducts respectively. However, it was the upstream wall, that is the rock pillar between transformer hall and downstream surge gallery, which was lacking sufficient thickness, and it was further weakened by intersection by the shear zone and thereby making it a pre-cracked rock pillar. This slide shows the intercept of shear zone in the crown of Downstream Surge Gallery. The rock support for the Downstream Surge Gallery were initially designed before the start of excavation, when the shear zone cutting the Downstream Surge Gallery was not encountered and was thus not known. This rock support system comprised of 200 mm thickness of SFRS and 8 to 10 meter long rock bolts at 1.5 meter into 1.5 meter spacing. The rock mass conditions at that time in Downstream Surge Gallery were considered as fair to good, as was made known in the geological report of geological consultant. As the excavations in Downstream Surge Gallery proceeded further in its benching, the shear zone was seen to be cutting the both walls of Downstream Surge Gallery, and the shear zone was traversing at steeply dip of 45 to 60 degree north, 30 degree east. In November 2014, benching had reached at elevation 608.5 meter. At that instance, subsidence of 55 mm occurred from RD 130 meter to 170 meter in downstream wall, and a subsidence of 20 mm was seen in upstream wall from RD 170 meter to 180 meter at elevation 618 meter. The design of rock support in the walls after the encounter of the subvertical shear zone in the walls was changed to an addition of concrete cladding on the shear zone intercept with 15 meter long rock bolts provided of 36 mm diameter to stitch the intercept portion of the walls. The concrete cladding added at the stretches of intercept of the shear zone in both the walls of Downstream Surge Gallery, though were provided with rows of two sets of rock bolts to stitch the top and bottom layer of the shear zone intercept. However, the end anchorage to be provided for one set of the rock bolts was always located in shear zone or fractured rock mass following the shear zone. Thereby, the efficacy of that set of rock bolts in the rows provided and designed for stitching the shear zone were not very effective. The designed treatment for strengthening the walls of Downstream Surge Gallery at the locations of intercept of the walls by shear zone must not have been based on a 3D numerical analysis, as before 2018 there doesn't seem to be having performed any 3D numerical analysis. Therefore, the arrangement of providing 15 meter long rock bolts in two sets, of which sets one kind of the rock bolts were having their end anchorages lying in fractured rock mass, obviously proved ineffective as seen in the 3D analysis done in year 2018 later by NIRM. The shear zone with a dip of 45 to 60 degree, orientation north 30 degree east, intersected both the walls of Downstream Surge Gallery, starting in its crown from RD 130 meter, extending throughout the depth of the Downstream Surge Gallery, continuing up to RD 180 meter. This intercept of shear zone in the walls had cut the Downstream Surge Gallery into two blocks, southern block and northern block. The northern block, which followed the shear zone, comprised of very poor to poor rock to a RD of around 210 meter. This reach in the northern block formed a hanging wall which comprised of highly jointed and fractured rock mass. During the period April 2014 to February 2016, the designers were requested many times to revise the rock sport designs in consideration of this actual geological conditions, which were actually poor to very poor in contrast to the earlier considered fair to good rock conditions. Not agreeing to bifurcate the Downstream Surge Gallery into smaller chambers, the designers did not even agree to provide wall beams and cable anchors to strengthen the rock pillars and the crown, as was suggested by the project management. This slide shows a typical correct design approach for large caverns in highly fractured rock mass. As was indicated earlier in 2014 in a numerical analysis done by civil contractor who was constructing the powerhouse complex in the project, that there will be widespread yielding in both walls of Downstream Surge Gallery as benching would progress. Therefore, the management had suggested the designers to either bifurcate the Downstream Surge Gallery into smaller chambers, which was not agreed to. Thereafter, the management suggested to provide wall beams at the SPL and cable anchors in the crown through this suggested wall beams and throughout the depth of Downstream Surge Gallery walls to strengthen and provide structural stability to the Downstream Surge Gallery. This was not adopted by designers, whereas it was quite known by that time that rock pillars are sheared and are behaving like a pre-cracked section. The authors Hook and Brown, in their book titled Design of Underground Excavations in Rock, suggest to provide cable anchors, as it is mentioned that cable anchors are particularly effective to improve the stability of the underground excavation, which face instability due to adverse geology in hard rocks which are faulted and jointed and which have several sets of discontinuities steeply inclined. The reach in Downstream Surge Gallery, starting from RD 130 meter to 170 meter or so, comprised of highly jointed and fractured rock mass, and therefore the provision of cable anchors was definitely warranted. The designs provided at locations of shear zone class 5, class 4 have only been rock bolts, and as informed earlier, one set of which were held with their end anchorage in sheared or fractured rock mass. This may have been too less a treatment to withstand shearing forces put by the structural features. A 3D numerical analysis of Punatsangchhu-II powerhouse complex, which was badly needed and based on which the design of rock sport system in the three caverns should have been carried out, was actually done 2 years after the rockfall in 2018 by the renowned institute NIRM. However, this 3D analysis was also based on a lesser representation of joint sets. The 3D discontinuum model analysis of the powerhouse complex was carried out upon request in 2018 by the National Institute of Rock Mechanics, that is NIRM, incorporating the various parameters like rock properties, rock mass joints, rock support and rock reinforcements, and the sectional profiles as considered by the design consultants in their designs, which was based only on the geological investigation report of the consultants done much earlier. However, as experienced during the excavations and informed by the geological interpretation made by the resident geologist of contracting agency for construction of powerhouse complex, there were other additional distinct prominent joint sets present which were not represented in the designs as well as in the 3D numerical analysis done later in 2018 by NIRM. These other joint sets, comprising one set dipping vertically oriented north 40 degree east and another dipping 50 degree oriented north 55 degree east, and the other set dipping 40 degree and oriented south 65 degree west, are not represented in the 3D numerical model. The representation of actual joint sets, including these additional joint sets, would have definitely made the 3D numerical analysis result in finding the scenario of excavation of downstream surge gallery further more critical and much more unsafe. The 3D analysis done by NIRM in 2018 ratifies that the rock pillars in the hanging wall side stood widely yielded. The analysis shows that without the provision of wall beams and cable anchors in the insufficiently thick rock pillar intersected by the shear zone, dividing it into two pre-cracked blocks, the upstream rock pillar and the downstream wall of the downstream surge gallery between RD 145 meter to RD 195 meter stood extensively yielded up to a depth of 15 meter into their thickness, with the strength to stress ratio of 0 in the yielded reaches. This slide shows the stage of excavation reached in the three caverns on 2nd March 2016, when the rock mass failure had happened in the downstream surge gallery. Each stage of excavation was properly provided with the designed support measures, adopting best engineering practices and standards. At the time when the failure had happened, the powerhouse cavern had been fully excavated to its total depth. Transformer hall was also fully excavated. The bus ducts were fully excavated, connecting the powerhouse complex and the transformer hall, thereby there were large openings in the downstream wall of the powerhouse and the upstream wall of the transformer hall. All the 6 draft tubes were also excavated through their lengths, but they were yet to be excavated to that depth where they entered into the Downstream Surge Gallery. Thus, the Downstream Surge Gallery had been excavated to a depth of 35 to 40 meters against its full depth of 58.5 meter. In the 3D numerical model constructed by NIRM, the excavated depth of Downstream Surge Gallery is taken of 35 to 40 meter only, which is the actual excavated depth at the time of Downstream Surge Gallery when the failure had happened. This slide shows the yielding of rock mass present in the north side of the shear zone all along the traverse of the shear zone in the hanging walls of the Downstream Surge Gallery. As was earlier informed in 2014 through the numerical analysis done by the contractors of the powerhouse complex and also ratified later in the numerical analysis done by NIRM, that when the benching excavation had reached in the Downstream Surge Gallery to its critical depth of 2/3 the height of Downstream Surge Gallery, to a depth of around 30 to 40 meters, widespread yielding had occurred in walls of Downstream Surge Gallery. As a result, a cavity of 91 meter height, 70 meter length and 45 meter width formed to the Downstream Surge Gallery's crown 3 years after the excavation had started. This slide shows the location and shape of the huge cavity that was formed in the crown of Downstream Surge Gallery in the reach of the hanging wall in the north side of the Downstream Surge Gallery, where the rock conditions were poor to very poor. The in situ measured vertical stresses before excavation in the Downstream Surge Gallery is 4.14 megapascal. The in situ maximum horizontal principal stress is 4.02 megapascal and minimum horizontal principal stress is 2.99 megapascal. The direction of maximum horizontal principal stress is north 17 degree. The longitudinal axis of Downstream Surge Gallery is oriented in north 10 degree east, which is almost parallel to the direction of maximum horizontal principal stresses. The hanging wall side of Downstream Surge Gallery, situated between RD 136 meter to RD 195 meter in the north of shear zone, comprised of rock blocks assemblage with their joints filled with fractured and crushed material. Thus, the rock mass in hanging wall has a large variability of strength compared between the intact rock and the rock mass. The uniaxial compressive strength of the intact rock is 55 MPa. The uniaxial compressive strength of the 3.5 meter thick shear zone is 3 MPa. The uniaxial compressive strength of the rock mass in the hanging wall is only ranging between 1.08 to 2.84 MPa. The strength of rock mass is reduced to a value of 2 MPa, whereas its constituent intact rock is having strength of 55 MPa. That is due to the fact that the rock mass in hanging wall is excessively jointed with joints filled with fractured and crushed material, which makes the rock mass very weak. Let us review the principal stresses in the Downstream Surge Gallery in its excavated state in a reach starting immediately after the shear zone towards the north in the hanging wall portion. The results of the 3D numerical analysis carried out in 2018 by NIRM shows that the value of major principal stresses which are aligned parallel to the longitudinal axis of downstream surge gallery in this reach of hanging wall were marginalized to a value of 2 MPa after excavation had reached to a depth of 35 to 40 meter in downstream surge gallery as compared to the value of the in situ major principal stresses of 4.02 MPa that were before excavation present in this reach. The major principal stresses in the downstream surge gallery in the hanging wall portion thus has its value just equal to the uniaxial compressive strength of the rock mass. The relaxation zone above the crown of downstream surge gallery is seen extended to a height of around 100 meter above the crown. The fact that the major principal stresses are developed to a value of 7 MPa in the near vicinity of the crown in its limited thickness proves that the arch action stood very much developed in the crown in the hanging wall portion of the DSG also, which is pre-stressed by rock bolts. This slide shows the plot of major principal stresses in a reach from RD 136 meter to RD 195 meter or so. It shows that the trend of marginalization of major principal stresses to a value of 2 megapascals is seen continuing from RD 136 meter to RD 195 meter or so. The size and shape of the relaxed zone developed above the crown in this hanging wall reach of downstream surge gallery between these RDs of 136 meter to RD 195 meter is peculiarly similar to the size and shape of the cavity developed during the massive rock mass failure which happened on 2nd March 2016, as would be seen in the slides coming after. As the rock mass condition stood improved in the northern side in the downstream surge gallery beyond an RD 196 meter, therefore the value of the major principal stresses developed in the reach of downstream surge gallery beyond RD 196 meter are seen to get back to the value of 5 to 8 MPa in the rock mass above the crown and in the location of the arch formed due to the pre-stressing achieved by the rock bolts provided in the crown in this reach. The existing state of stresses around an excavated underground opening are very important for the stability of the underground openings. Moderate stresses around an excavated section are usually favorable for its stability. Low stresses around the excavated section are often unfavorable for the stability. In the present case of downstream surge gallery of Punatsangchhu-II hydroelectric project, the major principal stresses in the downstream surge gallery cavern are oriented along the direction of longitudinal axis of the downstream surge cavern, but it does not provide confinement at interface with shear zone in the hanging wall. The in situ stresses being more than the rock mass strength has resulted the rock mass in joints to be fractured and crushed, thus making rock blocks present in the hanging wall prone to displacements. Whereas the minor principal stresses present in the downstream surge gallery cavern are oriented along direction of transverse axis of the downstream surge gallery cavern. The layout of cavern was such that minimum principal stresses, that is the minor principal stresses, are so oriented which provide confining pressure to retain arch action in the crown of downstream surge cavern. So if moderate minor principal stresses are present in the transverse axis of the downstream surge gallery cavern, they will make the downstream surge gallery cavern stable. And if the stresses are low in the transverse axis of the downstream surge gallery cavern, that is, if the minor principal stresses are low or tensile, then the stability of the downstream surge cavern would be jeopardized. So as we realize that the downstream surge gallery cavern is so oriented that the major principal stresses are parallel to the longitudinal axis of the downstream surge cavern, thus we learn that it is the minor principal stresses which are aligned in transverse direction to the axis of cavern would be responsible to confine the rock mass and be effective in producing arch action in the crown. Moderate minor principal stresses would be favorable for the stability of the downstream surge gallery cavern. So it becomes important to find out what is the state of minor principal stresses in the excavated section of downstream surge gallery. However, before we actually take a note of the state of minor principal stresses around the downstream surge gallery cavern of the Punatsangchhu II project, let us understand the role of hanging wall and the presence of lower valued stresses around an underground opening as to how much critical low valued principal stress and the influence of an hanging wall could be for stability of an underground opening. There is an international journal of rock mechanics and mining sciences which discusses the issue of progressive ravelling. A very good paper is published in this journal titled Stress, Instability and Design of Underground Excavations, authored by Martina Kasserer and Christiansen. Sorry if my pronunciation of the names is not correct. The paper shows a plan view of open stopes and the stoping sequence here given in circle numbers. The stop number 3300 was stable until mining of its adjacent stop number 3400 commenced. There are two principal stresses, sigma 1 and sigma 2, shown as acting on the boundary of the excavated sections. There is a hanging wall present in the stop 3300. This slide shows illustration of a typical bulk mining stope like the one in this case study, the stope number 3300. The stope has a footwall and a hanging wall and two drifts, one at bottom and one at top. There is a top sill. The overall massive sulfide ore zone at the depth in this case study was 300 meter along strike and 45 meter in width from footwall to hanging wall and dipped between 65° to 85°. So the geometry of the hanging wall, which is dipping at 65° to 85°, has a crucial role to play for the stability of stop number 3300. When we'll see how it, in combination with the low stresses, it behaves for the stability of the stop. The diagram on the right side is showing the plan of stops and the sequence of excavation. Stop number 3, that is 3400, is in continuation to the earlier excavated stop number 3300. The transfer stops discussed in this paper are mentioned to be averaged 35 meter in width, 45 meter in length, and over 180 meter in height. The paper states that experience at the mine indicated stops of these dimensions were stable. However, number 3300 stop, which had similar good quality rock mass conditions, experienced significant hanging wall problem, which was dipping at 65 to 85°. The hanging wall rock mass consisted of blocky noterites with one subvertical joint set at approximately 1 meter spacing and a second set of horizontal continuous joints also approximately at 1 meter spacing. These fracture sets formed potential wedges in the hanging wall and back of stops. However, simple wedges do not usually lead to progressive ravelling, particularly when the geological strength index ranges from 60 to 85 with compressive strength 25 to 100 MPa and tensile strength of minus 0.4 to minus 2.65 MPa with a modulus 27 to 80 GPa. These simple wedges would have not led to progressive ravelling, the paper mentions. It is interesting to see that why the stop number 3300, despite having good quality rock mass conditions with joint sets forming simple potential wedges, would suffer a progressive ravelling. Stop number 2900 and stop number 3300 were excavated lying independent of each other. That is, a stop number 3200 lying between stop number 2900 and stop number 3300 was not excavated before ravelling failure occurred in stop number 3300. Mining of stops number 2900 and 3300 was carried out without incident, with stop number 3300 remaining open and stable for approximately 1 year. The mining of stop number 3400, which was an extension of stop number 3300, was coincident with the ravelling of the hanging wall of stop number 3300. The adjacent figure shows that because of the stop geometry, a zone of relaxation extended several tens of meters into the hanging wall of the stop number 3300, but only after stop number 3400 was excavated. The diagram shows a vertical section through stop number 3300, looking towards the mine's west, and it shows contours for stress sigma 3. We see that sigma 3 in the shaded area ranges from -1 to 0, and this shaded area is exactly the location of Ravelling. With the sigma 3 ranging from -1 to 0 in this shaded area, there was loss of confinement occurring in this area, and a cavity in the hanging wall was formed. It is evident from the figure that failure or ravelling had occurred in the zone with a confining stress becoming less than 0. That is, the confining stress when becomes tensile, ravelling can occur. The confining pressure also influences the ductility of the rock mass. The higher the confining pressure, the greater is the ductility observed of the rock mass, and it is true vice versa. That is, lesser the confining pressure, the rock mass would have lesser the ductility. The behavior would be more brittle if the confining pressures are less. This results in a quick vicious circle of ravelling failure, that when the confining pressure would become tensile, the ravelling would occur, and as ravelling will progress, the increase in the strain rate would make rock appear more brittle. So therefore the ravelling failure would be very sudden and brittle. The paper Stress Instability and Design of Underground Excavations, after pointing out that ravelling would occur when the confining pressure will become very low or tensile, and the progress in ravelling will make with the strain rate increasing, the rock appearing more brittle. The third thing that the paper establishes is the extent of depth of the failure. It mentions that in the structurally controlled gravity-driven process leading to wedge-type falls of ground in underground excavations, it is actually the variability in rock strength rather than stress that is responsible for the frequently observed variability in depth of failure and failure mode. If there is more variation in the rock strength of the rock mass, there will be more depth influenced by the ravelling failure. The paper titled Stress, Instability and Design of Underground Excavations, discussed in the previous slides, is available at the website sciencedirect.com. We learned from this paper that a ravelling failure in the rock mass would occur when the following engineering geology conditions would exist in an underground excavation. That is, if firstly the rock mass is blocky, comprising numerous joint sets. Secondly, these fracture sets should form potential wedges. Thirdly, there should exist a significant problematic hanging wall problem. Fourth, the confining stresses in the hanging wall, if becomes less than zero, that is if they become tensile, then a ravelling failure would occur in that rock mass. The paper also establishes that if the geometry of the inclined discontinuities present in the rock mass are conducive to gravity induced and structurally controlled fall of the blocks of the rocks in the hanging wall, then the potential wedges formed from the numerous joint sets in the problematic hanging wall would result in a ravelling failure with confining stresses becoming absent. The paper also mentions that the variability in the rock mass strength, if is present, it will guide variability in depth of failure and mode of failure also. From the previous slides discussing the state of geological conditions, engineering geological conditions, and the state of stresses in the excavated downstream surge gallery, it has been established that the rock mass is very much blocky in the hanging wall portion of the downstream surge gallery. It has also been established that there are multiple fracture sets which form multiple potential wedges. It is also seen that there is a significant problematic hanging wall problem in the northern portion of the downstream surge gallery, separated out by the presence of the major shear zone, which is dipping very much subvertical. So the first three conditions have been seen to be existing in the set of prerequisites of progressive ravelling. Also, it has been seen that the geometry of the inclined discontinuities comprising numerous joint sets are such that they form potential wedges which are conducive to gravity induced and structurally controlled fall of the blocks if there were no confining stresses present in the crown of the excavated downstream surge gallery. It is also established that there are huge variability in the rock mass strength between the strength of the parent rock blocks and the infill material in their joints, and due to the presence of various weak and fractured rock mass, the depth of failure would be guided by this variability of the rock mass strength. So out of this set of prerequisites, the only prerequisite that remains to be seen is whether the confining stresses in the hanging wall had become less than zero, that is tensile. The authors Hook and Brown mention in their book titled Design of Underground Excavations in Rock that heavily jointed rock mass behaves like an assemblage of interlocked angular particles with no significant strength under unconfined conditions. It may be noted that the rock blocks comprising the rock mass in the northern side of shear zone forming the hanging wall were comprised of regular and planar joints and surfaces of blocks. with all other prerequisite conditions having been met, the heavily jointed blocks in the yielded rock mass in the crown of the downstream surge gallery were just in the waiting for a trigger to happen, which can cause the rock mass to behave as mere an assemblage of the rock blocks and result in a ravelling fall of rock blocks one after the other. The removal of the confinement pressure, which was being exerted so far by the minor principal stresses till a particular stage of excavation in benching was reached, would provide that trigger by loosening the rock blocks and start ravelling of the rock blocks. It was earlier noticed in the previous slides that since the direction of the longitudinal axis of the downstream surge gallery is almost parallel to the direction of major principal stresses present in the excavated sections, it would be minimum, that is minor principal stresses, which are acting in transverse direction to the axis of the downstream surge gallery cavern, would be responsible to provide the confining pressure to the assemblage of rock blocks of the rock mass in the crown of the downstream surge gallery in order for it to generate the arch action in the crown. However, the 3D numerical analysis performed by NIRM in 2018 establishes that the confining pressure in the crown of downstream surge gallery is absent in the reach of the hanging wall in the downstream surge gallery. The transverse minor principal stresses extending into tens of meters above the crown in downstream surge gallery in the hanging wall in this stretch had become tensile or are very low. The following two slides show the plot of minor principal stresses present in the excavated sections of the downstream surge gallery from RD 146 meter to RD 216 meter. The minor principal stresses in this entire stretch of the hanging wall are tensile or are very low above the crown, extending to tens of meters above the crown, and in fact the same problem is seen in all the three caverns, that is of powerhouse cavern, transformer hall cavern and downstream surge cavern. But the major difference between these three caverns is the presence of the major shear zone, which cuts all along the depth of the downstream surge gallery only and does not cut the powerhouse or the transformer hall in a significant length remaining affected by the shear zone. The shear zone merely touches or cuts the powerhouse and transformer hall caverns near their gable end. Therefore, the confining pressures are present from the major principal stresses in these two caverns, whereas we have seen that the major principal stresses have also been reduced to very low value above hundreds of meters above the crown of downstream surge gallery in the hanging wall reach, and now that the minor principal stresses are also seen to have reduced to very low value or tensile in nature. The confining pressure for the assemblage of rock blocks in the downstream surge gallery has become absent. So we see that though the minor principal stresses are turned to tensile stresses in all the three caverns, that is of powerhouse cavern, transformer hall cavern and the downstream surge cavern, but it is only the downstream surge gallery that has the presence of a subvertical major shear zone cutting it right in the middle of its length, which makes a problem of hanging wall present only in the downstream surge gallery. This plays a major role in the instability of the downstream surge cavern, and we see that the major principal stresses, as was shown in the previous slides, had got reduced to marginalized value above the crown in hundreds of meters of height in a shape of a balloon kind of shape, which was not the case in the powerhouse and transformer hall cavern. The major principal stresses were having significant value above the crown in transformer hall and in the powerhouse cavern. So it is only the downstream surge gallery where the hanging wall problem is present due to the shear zone cutting it throughout its depth in the middle of the length of the downstream surge cavern, that the major principal stresses are marginalized to a great depth above the crown to hundreds of meters of length in a shape of a balloon kind of, and the minor principal stresses have also become tensile in tens of meters of height above the crown. This slide shows the sectional plan of the downstream surge gallery at SPL level, which establishes that in the widespread stretch in the hanging wall to the north side of the downstream surge gallery, the minor principal stresses are reduced to sub-zero, that is tensile in nature. As discussed in the earlier slides, that due to the presence of multiple set of joints filled with fractured and crushed material, the rock mass in the hanging wall behaved like an assemblage of rock blocks. This assemblage of rock blocks remained together till the confining pressure was present around them. With the progress in the excavation depth in the downstream surge gallery, at one stage the confining pressures provided by the minor principal stresses and the major principal stresses have been found to either becoming tensile in the case of minor principal stresses and marginalized in the case of major principal stresses. Thus, the assemblage of rock mass had become unconfined and there were displacements happening in the hanging wall below the SPL level in the walls of the downstream surge gallery, which assumed the values of 65 mm to 100 mm in both the walls of downstream surge gallery. the increased rate of displacements in the rock mass made the rock mass behave more and more brittle as it was learned that with the increase in the rate of strain, the rock mass behaves more and more brittle. It was discussed in the published paper of Stress Instability and Design of Underground Excavations. The displacements at the SPL level in both the walls of Downstream Surge Gallery had attained a value of 100 mm, which caused rock blocks at the bearing level of the crown getting dislodged and thus making the crown fail in its bearing. The instrumentation observations available also ratify that the pace of displacements in the crown and walls had increased with the progress in depth of benching. On 2nd March 2016, settlement in the walls had reached suddenly to 96 mm when the benching level had reached to elevation 590 meter. This slide shows the arrangement of instrumentation in Downstream Surge Gallery at center of its crown and at the SPL level and in the walls of the Downstream Surge Gallery. This slide shows a table mentioning distress in crown at elevation 620 meter in Downstream Surge Gallery, downstream wall at RD 135 meter with respect to progress in benching. And this is a typical slide, and similar behavior is seen at elevation 620 meter, that's PL of the crown, in the throughout stretch of hanging wall in the north of the shear zone. The first row mentions the date of observation of instrumentations. The second row mentions the benching level of excavation reached on the particular date. The third row shows the surface movement as captured by the surface targets, and fourth row shows the stress level achieved in the load cells on those particular dates embedded at level of 620 meter, and the remaining rows shows the readings at various points of anchorages in the MPBX installed at elevation 620 meter in the wall at the anchorages positioning 5 meter, 10 meter, 15 meter, 20 meter and 25 meter into the wall. We see from the table that though the MPBX readings and the load cell readings do not show significant distress, but the surface movement observed from the surface targets show a steady increase in the displacements with a progress in the depth of benching. Suddenly we see that the MPBX readings also jump to significant values, and the load cell also registers a higher value of stresses when the surface movement is suddenly seen on 2nd March 2016 as compared to the previous observations till October 15, that the settlement and the drift towards northern direction and the horizontal displacements had attained much higher value of 27 mm, 96 mm and 16 mm respectively in X, that is the transverse direction, Y, that is the vertical direction, and Z, that is the longitudinal direction from south to north. This table shows that there was a significant bodily shifting happening at the SPL level of the crown with respect to the lower portion along the traverse of the shear zone. Thus, we see that all the prerequisites for a progressive Ravelling failure were present in the case of Downstream Surge Gallery cavern when the benching depth had reached significant levels, that with the rock mass being blocky comprising numerous joint sets, the fracture sets did form potential wedges, and with the presence of problematic hanging wall problem, the confining stresses had got reduced to very low value and also becoming tensile over tens of meters above the crown, and the geometry of the inclined discontinuities presented by the numerous joint sets guided the gravity-induced structurally controlled fall of the blocks of the rocks in the hanging wall, and as there was a variable strength to a great extent between the parent rock mass and the infilled material in the joint openings and presence of fractured rock mass, that the Ravelling failure was guided to extend to greater depths above the crown. It is significant to note that the lack of confinement pressure led to increased strain rate, and thus was the loss of ductile behavior seen. It all resulted in vicious circle of Ravelling failure, as exactly as discussed in the paper Stress, Instability and Design of Underground Excavations, discussed in earlier slides. It was mentioned in the paper that the higher the confining pressure, the greater the ductility observed. Increasing strain rate makes rock appear more brittle. The absence of confining pressure and presence of zone of relaxation of major principal stresses extending in tens of meters in the crown resulted in fallout of rock blocks in a succession, one after the other. The resulting increase in strain rate made the rock mass more brittle. Thus, cycle of Ravelling brittle failure of rock mass happened progressively with increased suddenness instantaneously. This slide shows the three-dimensional view of the Downstream Surge Gallery and the other two caverns, showing that how precariously it was only the Downstream Surge Gallery which was cut by the major shear zone, which was dipping subvertically at an angle of 45 to 60 degree in the middle reach of the Downstream Surge Gallery. It was the hanging wall reach falling towards the north of the shear zone where the confining stresses had become tensile and the rock mass comprised jointed and fractured rock of very poor to poor category. The Norwegian Geotechnical Institute was hired by the consultants after the rockfall in Downstream Surge Gallery to study the site and find out the reasons behind the fall. The Norwegian Geotechnical Institute has mentioned in its findings after the study that it is believed that steel ribs do not and will not provide any acceptable rock support. This is very well understood otherwise also that steel rib supports provide a passive support and the steel ribs come into action to provide a support only when the rock above the steel ribs in the crown subsides and puts load on the steel ribs. The second observation of the NGI was the ribs do not show any sign of deformation and all the ribs failed at the joints. Third observation made by NGI is the steel ribs do not show any sign of bearing the load from rock mass, whereas the rock pillars are more loaded. These observations imply that the ribs have not failed as a structural element. That means the steel ribs were not taking any share of the rock load till their failure, as is mentioned by NGI in this finding that the steel ribs do not show any sign of bearing load from rock mass. The other important finding to note is that NGI has found that it was the rock pillars which were more loaded and the steel ribs were not excessively loaded. Certain specific observations can be made on the behavior of steel ribs as seen from the state of the fallen steel rib parts. Firstly, steel ribs which are lying fallen down are found untwisted and have their arch shape intact. These bear, therefore, no sign of taking excessive load. Secondly, the bolts at the various joints of rig segments are lying intact after their having fallen down. Thirdly, the various rig segments are found separated at connecting joints with a joint plate welds broken. From these observations, it can be concluded that, as mentioned in the previous slide, that the steel ribs were not acting as a structural element, but they have failed due to a sudden impact loading being transferred to them at a particular time. The picture taken of the fallen rib segments are seen in this slide. It can be seen that there is no twisting seen in the fallen ribs, which indicate that the steel ribs had not been subjected to any sustained loading. In the present slide, it can be seen that ribs do not show any sign of buckling, which would otherwise be there if an elastic failure from excessive loading would have happened. These steel ribs are seen sheared at joint plates, indicating sudden brittle failure of their welds. The observation of the NGI that rock pillars were more loaded and ribs did not bear excessive load implies that the arch action in the crown of Downstream Surge Gallery, even in the failed reach, was intact, and the crown was able to successfully transfer the rock load, acting as a perfect arch of rock, transferring the load to the rock pillars without burdening the ribs beneath it with any load, until the failure of footwall support had happened. The fallen ribs are found untwisted and bear no signs of taking excessive load, ratifies the theory that the arch ribs had only eventually become unstable due to withdrawing of wall support beneath it. Due to impact of their fall, the ribs got broken apart at their segments, connecting joints, without even having been subjected to any excessive load. Further, simultaneous to the falling of ribs, as the arch formed in the rock mass of the crown was intact till the support from the wall on which the arch was resting got withdrawn because of the failure in the wall support. Along with the falling of ribs, the structurally controlled Ravelling failure of rock blocks in the yielded rock mass in the crown happened too. Immediately as the footwall support failed and withdrew the support provided to the arch in bearing. The following three important observations of NGI in their report corroborates the structural failure of rock mass. NGI has reported that the shape of cavity is controlled by the discontinuities. It also states that it is clear that the major mechanism of the rockfall was structurally controlled blockfall. Thirdly, it states the orientation of maximum horizontal stress is parallel with axis of the downstream surge gallery, which does not help to prevent the rockfall through confining on the rock blocks at the roof. In other words, the maximum horizontal stresses not able to prevent the rockfall. It was the minor principal stresses which were relied upon for providing the confinement to the rock blocks at the roof. The NGI has summarized on failure mechanism in downstream surge gallery that the rock mass in the footwall of the shear zone first started to move down because of the insufficient support and stress relaxation. It says that later on, as the key block in the footwall moved, the rock blocks at the hanging wall moved down flowingly. NGI's findings on footwall failure also ratifies what the instrumentation observations concluded. Instrumentation observation 2 indicate that the distress in the wall support to the crown in the reach of traverse of shear zone in the downstream surge gallery, that is from RD 135 meter to RD 195 meter, increased as excavation in benching progressed. The settlement in the wall at the support of the crown level was of 96 millimeter as on 2nd March 2016, when the benching had reached an elevation of 590 meter. So all along in the reach of traverse of shear zone in the hanging wall in the downstream surge gallery, the distress in the wall support, especially at the support level SPL of the crown, were increasing as the excavation progressed in benching depth. Assessment of the size of the cavity formed was done by using cross-hole tomography, and it revealed that the cavity size formed above the crown of downstream surge gallery was 91 meter in height and 70 meter in length and 45 meter in width. The extent of cavity formed was also confirmed using LIDAR technology using CMS 500 equipment. A similarity of the shape and size of the zone of relaxation as seen in the results of 3D numerical analysis done in 2018 to the size and shape of the cavity formed as captured by using LIDAR based cavity monitoring system with CMS 500 camera and by resorting to cross-hole seismic tomography connected at site is noticed. It is thus established that numerous potential wedges due to absence of confining pressure had resulted in the fractured rock mass to undergo gravity induced and structurally controlled fall of rock blocks in the hanging wall of Downstream Surge Gallery. The geometry of the inclined discontinuities further guided the gravity induced and structurally controlled fall of the blocks. It is significant to note that the shape and size of the cavity formed from the rockfall is identical to the shape of zone of relaxation seen in the plot of major principal stresses in the reach of the hanging wall, but was so seen only in the Downstream Surge Gallery and not seen so in powerhouse and transformer cavern, with minor principal stresses becoming tensile in the affected reach. Besides the 7 crucial technical lapses discussed in earlier slides, the 8th and very crucial lapse was in the administrative controls made for the project. All the project controls were empowered to the designers. This administrative lapse produced a major conflict of interests in the different roles performed by the designers, depriving the project of the various checks and balances to be applied in implementation of the project. The consultants of the project WAPCOS had their further design consultants Central Order Commission for civil construction designs and drawings, and Central Electricity Authority for electromechanical and hydromechanical designs and drawings, and Geological Survey of India to handle the geology investigations. From role of preparation of detailed project report, scrutiny and approval of detailed project report, preparation of tender specifications, preparation of tender stage designs and drawings, carrying out of construction stage investigations, preparing detailed designs for construction of the project, for carrying out the investigations to evaluate the problems faced during construction, preparation of solutions and the designs for resolving those construction stage problems faced in the project construction, and also scrutiny and approval of these solutions decided by the designers were also to be approved by the designers itself. So all these important rules were all empowered to designers, which deprived the project various checks and balances to be introduced at every level of project implementation. And this was a very crucial lapse which failed the project in carrying out proper geological investigations for preparation of detailed project report, for carrying out proper and adequate geological investigations to base the designs and drawings upon, to carry out the proper designs and drawings to be implemented at the project site, to evaluate the lapses in the designs and drawings, to evaluate the consequences and find the solutions of the problems faced in the project construction. All checks and balances to be performed in these roles were totally absent because all these roles were to be conceived, carried out, evaluated, scrutinized, and performed by one agency, designers, the Central Water Commission.